Hi. What we have done, uh, we are in chapter 2, first of all, linear algebra. We examined linear algebra. We have seen the axioms, we have seen the theorems of Boolean algebra. And then we examined a bit in detail Boolean functions, canonical expansion, Shannon theorem. Why we are dealing with Boolean function exceptionally? Because combinational circuits, mathematical model of combinational circuits are Boolean functions. Therefore, we are spending some time on it. So we have examined already. Now we're going to, in this video, we're going to examine an example, and I give you how to find a non-Boolean function and in this video. So let's switch from this one to in details. Move this down, take this in, and get this, and open board. Okay, so move it down. Here you are. Let's clear this area. So you see here, we've got a truth table. Truth table of a three-variable function, isn't it? Here, second, third, and fourth columns. That means these columns here. Show domain set. So this is for three-variable function. This is this set. So since in this case, the S has got two elements, 0 and 1 elements. So 2 to the power 3 is 8. So in this set, we've got 8 elements, 1, 2, come to here. So if you write it, these binary numbers in decimal, this is 0, and this ends up with 7, isn't it? That is 7. So you might consider is 0 to the power n minus 1. 8 minus 1 gives you this 7. So what is this? This is, we are talking about three-variable functions defined on these sets, while S has got these two elements. So this is this set here. Maybe I'll draw it in different color. Is value set, isn't it? So this set, that is. So this is the truth table. From this truth table, how we can represent a Boolean function. So in order to represent a Boolean function, represent, we said by Shannon theorem, we can say that Boolean functions can be written in two forms. One of them is you're going to write true minterms, add them up, or you're going to find the true max terms and multiply those max terms, or product those max terms. So we've got to write the minterms and max terms first. How we are going to write the minterm? We know it. This first column represents x1 variable. Second column represents x2 variable. Third column represents x3 variable. So this line here, x1 gets the value 0, x2 gets the value 0, x3 gets the value 0. The corresponding minterms is going to multiplication prime of these variables because these values are 0. So for the first, second tip canonical expansion, we have seen all that. I am just repeating here. So for the second line, for example, x1 and x2 gets the value 0, while the x3 gets value 1. Value 1 corresponding variable in the product term is itself. For the others, for 0 ones, they are primes here. So for the last one, since all of them 1, in the product term you see all these variables itself seen here. There's no complement in these variables. So similarly, for the sum term, we are going to do the opposite. If the variable gets the value 0, the corresponding variable in the sum term is going to x1, not the complement, but x1. Here, complement, but in here, x1. For the last one, for example, x1, x2, x3, all of them gets the value 1. So in the min term, the variables itself we see them. In the summation term, prime of these variables sum is my sum term. So from the truth table, we find the min terms and the max terms corresponding to this set elements, isn't it? So the next step, come to this next step, clear this area first. We're going to write the canonical expansions that we already seen by the end of the Shannon theorem that we showed. We said M0 is a min term, that's the coefficient of this min term. This coefficient represents this F0, 0, 0. And this, for example, 0, 0, 1. Function's value at that point. So these are all the min terms that we wrote in the previous page. In here, these are the values, function values corresponding to these points, which is 0. So I can show it, come back, look at this list. This is the function values in sequence 0, 0, 1, 0, 1, 1, 0, 1. So we're going to see the same thing here. 0, 0, 1, 0, 1, 1, 0, 1. That's the function values that we see in the truth table, last column. So these coefficients are going to be multiplied, these min terms. Now, when you see the value 0, 0 multiplied with something gives you 0, isn't it? That's going to be 0. This is also going to be 0. And this is going to stay there. 1 multiplied something gives you M2. So 0 multiplied something, that gives you 0. And that gives you 0. For the other ones, the coefficients are 1. But the 1 multiplied something give whatever it is. That's the axiom. So what is left is M2, M4, M5, M7. These are the true min terms. That means the coefficient of these min terms has got the value 1. These are the coefficients. Let me show this coefficient here. That coefficient, that coefficient, that coefficient, and that coefficient. So I wrote here the true min terms of which coefficients are 1. So these are the true min terms. Summation of the true min terms gives me the function. So the min terms, they were in this page. So M1, M1 is function value 1, M4, M5, and M7. So these are the min terms, true min terms for those. So you see those true min terms here. So that is the representation of this function, isn't it? So you can say this expansion, so we wrote this truth table given function here in this form by using the Shannon theorem. So this is called first canonical expansion or sum of products. These are the product terms. So all these product terms are being summed here. So sum of products expansion, or first canonical expansion, we call it. So once we have seen it, we can represent this function in another way. How we are going to represent it? These are the function values equal to 1 cases, isn't it? So if I write all this in decimal, so that 1 is M2, isn't it? M2 is 0, 0, 1, 0. That is M2. So this corresponds M2, 2. And then M4, 4, M4, 4, M5, and M7, isn't it? So if you write these decimal numbers underneath the indexes of these true min terms in here, that is another representation of the same function. This function can be represented by this. How we are going to read it? Easy. For these points, function gets the value 1. So if you consider the second expansion that we seen theoretically, so this is the example of it. If we apply this to our example, so we are going to write this function, consider this, we will talk about this later on. So this function, our function, 3-variable function, second expansion, Shannon theorem's second part, is this. You might call it the dual of this expansion. So in here we've got f0 plus m0, that's max term. That is a sum term. Multiplied with another sum term, f1 plus m1, it goes like that. So we already know that this is equal to 0. M1 is also 0, so that is 0 as well. And that is 1. That is 0. That is 1. That is 1. That is 0. And that is 1. What I have done here, I wrote the function value in sequence. That means this column here, 0, 0, 1, 0, 1, 1, 0, 1. 0, 0, 1, 0, 1, 1, 0, 1. I wrote that. So how I'm going to go forward? So 0 plus m0 gives you m0, isn't it? So the result of this, let me to use different color. So this is going to be in. If you come, this is going to be in as well. If you come to this one, 1 plus something, we already proved in a theorem that 1 plus something gives you 1, whatever it is. So the result of this is 1. 1 multiplied something does not affect the multiplied term, so this disappears. In here, 0 coefficient 1 min terms disappeared. In here, 1 coefficient max terms disappear. So this is going to disappear, this is going to disappear, and this is going to disappear. What is left? So you might say here, this is going to disappear, 1 disappear, 1 disappear, 1 disappear. What is left is this, 0 coefficients are left. We didn't put 0 here because 0 something give you whatever you summed with. So that gives you m0, that gives you m1, m3, m6. So how we're going to read it? We said if the coefficient of a max term is equal to 0, this is called true max term. So this is the multiplication of true max terms, or product of true max terms. So this is called, so if you go to the previous page, these are the whole max terms. The true ones are this one, 0, 1, 0 coefficient 1, this one, and this one. What are they? This 6, that is 30136. Here you are, 0136. So true max terms. So the corresponding max terms are those. So this is the second, this is called second canonical expansion or product of sums, isn't it? These are the sum terms, product of these sum terms it is called. Now let's come to the next one now. Clear this area. So what we have done up to now in this example, we had a truth table, a function given as a truth table, and we said in general true min terms, summation of the true min terms gives you the function, or the true max terms multiplication gives you this. Alternatively, we said you can write the true min terms indices in decimal here, true max terms indices in decimal here. So now answer to that questions. Let's try to answer to these questions. How many different representations are there for a Boolean function? One of them is this. You can use the sets and show you the relation between a set to the s to the power n and s. If s has got 0 and 1 elements only, so it's going to be 2 to the power n element here and 2 elements here, 0, 1. So that these are the numbers, these are these things here. So if you do these relations, if you show these relations for each functions, you can show that. In our example, that's going to be S3 to S. So S3 set is going to be this 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is S3 set. And this set here is 0, 1. So how was it? 0, that was 0, that was 0, and that was, let me say, 0, 1, here you are, 0, 1, 3, 0, and 6, 0. And for the other ones, different color. So for this one, 1, for this one, 1, for this one, 1, for this one, 1. So this is the given function for us. That is the set representation of a Boolean function. The second representation is this table, x1, x2, x3, f, 0, 0, 0. You got a 1, 1, 1, and write the function values here. So that is the truth table representation. This set representation. So, and then in the previous page, this is another representation. Let's say this is the third one, product of sums, and this one, sum of products, that's the fourth one, and that is the fifth one. Write in decimal the 1 points here with the summation symbol, and this one, sixth one. So we have seen 6 different representation of a Boolean function. Which one is simple? If you ask this, that is it. You see, that is a simple one. That's a simple one. So you can see it here. If you write this, how are you going to transfer it to our function? You're going to say that because of that sum here, that 2 in binary is this, 4 is in this, 5 is this, 7 is this. So for those points, function value is equal to 1. For the other points, function value is equal to 0. Once you give me that, I can easily tell you this. Then I can find the first canonical expansion easily. So this simplest representation of the Boolean function is this. It is just one line, not many lines like that, not many lines like that. It is just one line, represent the whole function. Whatever the variable number is, isn't it? This is independent from the number of variables. You're going to write just one line to represent a Boolean function. That is good news. Let's come to the last slide. In the last slide, I would like to show you many times, maybe in general, I said there are some Boolean functions and non-Boolean functions as well. So this is a good example for you to find out a Boolean function, non-Boolean function by using a Boolean function. Now we already know that cardinality of S, that means the number of elements in this set S. Assume that this is capital N. When the capital N is equal to 2, what happens? It is written here. If it is capital N set to the power, if you got n variable functions that you're going to define, so the number of elements in this set is n to the power small n. Capital N is the number of elements in this set. N is the number of variables. So you've got that number of elements. So if you define a function between these two sets, the number of functions that you can define here is n to the power small n. So these are the functions, the whole total number of functions. This shows you Boolean functions, number of Boolean functions that you can define. Why it is this? Because in the Boolean functions, only 0 and 1 points included lines, once they are known, all the other points corresponding function values can be calculated by using the Shannon theorem. Therefore, the number of Boolean function is equal to this. And then number of non-Boolean functions, these are the Boolean functions. Sorry, these are all total number of functions. These are the Boolean functions. The difference between those two gives you the number of non-Boolean functions. Now, there is a good, interesting solution here. If capital N is equal to 2, then it's going to be all the functions are going to be non-Boolean here, are going to be Boolean. So the difference, so that means n, capital N equal to 0, then this is equal to this, isn't it? These are the number of Boolean functions. These are the total number of functions. The difference is 0 non-Boolean functions. So conclusion is, very good conclusion is this. When the set has got 0 and 1 elements only, any functions that you can define from S to the N to S, all of them Boolean functions. What does this mean? All the functions can be written as a formula, as we said already, can be represented in 6 different forms. Now, how we can find a non-Boolean functions from a Boolean function is an example here. So in order to talk about a Boolean functions, the set S must be different from 0, 1 element included. So this, let's say our set is 0, 0, AB. If set has got 0, 1 values only, all of them Boolean functions. Now in this case, some of them, they are non-Boolean functions. So this example is I'm going to show you how to find a non-Boolean function by using a Boolean function. Now here, these special points, this is a 2 variable function. These are the special points that we deal with in Shannon theorem. So for these special points, Boolean function value is written here. So we can write this Boolean function as a formula like that. I know this is a Boolean function. So if you've got 4 elements like that, if you are defining 2 variable functions, so it's going to be like that. So the number of elements in S is going to be 4 to the power 2. So that is 16. This 16 points here. So this is S square when S has got these elements in it. So all of them written here, these are the special points here. So my Boolean function has got this coefficient here in this expansion I wrote here. So at that point, my function, this Boolean function value at that point is going to be calculated by replacing x1 with 0, x2 with a. x1 0, x2 with a. So x1 0, x2 with a. So in here x1 prime, since x1 is 0, prime of it is 1, x2 a. The last term b times x1 0, x2 a. So I'm talking about this. So for this point, my Boolean function value is a. So this is a. We just found a. Okay. So if you repeat this for all the other points, you're going to end up with this. So this is f1 is our Boolean function. I wrote this Boolean function. Once I know these special points values, for the other points I calculated it and wrote it here. So f2 here has got the same values for these special points, but in here I have changed it to make it 0. What it means, if it was a Boolean function, it was going to have that value. If it is different from that value, then this cannot be a Boolean function. So it's going to be a non-Boolean function. So f2 is a non-Boolean function here. So that is the end of this video then.